Hurricanes, hailstorms, tornadoes, and wildfires. These are just some of the weather hazards that displace families and disrupt lives. Many of us are familiar with the scenes of devastation these hazards cause, and the recovery process for affected communities can take months, even years. In the most extreme circumstances, some may never be whole again. This may prompt many of you to ask, what's being done to reduce the risks associated with these hazards? To answer this question, the Insurance Institute for Business and Home Safety presents the Disaster Discussions podcast. Join me, your host, Armand Brody, as I sit down with professionals in the insurance, science, construction, and resiliency industries who will help us explore the intersection of these hazards with the built environment. We'll bring you in-depth conversations with experts from across the country and highlight how science is engineering real-world solutions for home and business owners to create safer, more resilient communities. Join us for these discussions every month. And to make sure you don't miss an episode, go subscribe to the Disaster Discussions podcast on your favorite podcast app. We also invite you to engage with us on social media, to ask your questions, share your thoughts, and to learn more about the IBHS mission. Welcome to the Disaster Discussions podcast, where we explore the intersection of weather and the built environment. I'm your host, Armand Brody from IBHS, and we continue. It's part 2 of our series from the Severe Local Storms Conference. Hopefully, you've had an opportunity to take in our first session, the interview with IBHS's Christina Gropp and Dr. Mackenzie Krochak from the University of Oklahoma Institute for Policy Research and Analysis. Great conversation there. Our conversation continues, our series continues here from the SLS conference with Dr. Matthew Kumjian from Penn State University. So here's the issue. When it comes to the economic impact of severe storms, hail might seem like the little brother to tornadoes and damaging winds. But did you know it's the greatest loss driver in total cost to insurers? The more we learn about the characteristics of hail, the more we can prevent losses. IBHS's Dr. Giammanco was joined by Dr. Matthew Kumjian, who uses weather radar to detect hail in severe storms. They'll discuss how this is helping to work towards determining the sizes of hail that may be present and how that relates to damage potential. Got a great episode, a great interview with Dr. Giammanco and Dr. Matthew Kumjian. Here it is right now.
Welcome back to our Severe Local Storms Conference of the American Meteorological Society series. We're going to hop back to the topic of hail today, following up on our podcast that we had with Julian Brimelow and the Northern Hail Project, joined by one special guest and a wonderful friend of mine who we've been working together for almost 7 years now, Dr. Matt Kumjian, Associate Professor of Meteorology at Penn State University. And we're going to talk a little bit about the future of hail and how we detect it and how we forecast it. So Matt, first off, I'm going to paint the picture where we are in terms of how we detect hail, but also how we forecast it.
Yeah, great question. And thank you very much for having me, for chatting about a topic that's near and dear to my heart, as you know.
Yes, it is.
For all of our work together. Starting from the forecasting perspective, basically the forecasters are going to look for the ingredients that come together in the environments that support the parent hail storms themselves. And so we know the basics about which types of storms produce the most prolific producers of damaging hail. But when it comes down to the details, that's where we kind of get a little bit, have a little bit of uncertainty, and that's where we've been focusing our research efforts.
We'll start into the radar detection side. So a lot of people know you see a severe warning and it says, hail up to $50 size or something like that. Tell us, how a forecaster at the National Weather Service would take that information from radar and actually I'll say try for now, try to assess the severity of hail within a given thunderstorm.
Sure. So just briefly, radars operate by sending out radio waves, and it bounces off of the storm, all the particles in the storm. And so they try to use that information in some way to determine what's out there, how severe it is. With the new dual polarization radar upgrade, we do have some information about the shapes and sort of physical composition of those particles. And that can give the forecaster some idea if it's small melting hail, which kind of look like big raindrops to the radar, or if the larger hail, it tends to tumble more. But then once it gets kind of above that sort of severe 1.5 inch threshold, it becomes much more difficult to determine the hail size. And so oftentimes they're basing on spotter reports or citizen scientist reports that are coming in about what sizes they get, and they can adjust their warnings accordingly. There are algorithms that are out there, but again, there's a lot of work that needs to be done to improve them.
All right, so let's stay with that. The two primary things we hear a lot about, both from the operational side and then the industry application, are the use of the MRMS mesh tool. So that's one. And then using the hydrometeor classification algorithm that's based on the dual pole products. So let's start with the MRMS, the maximum estimated hail size product. And then we'll talk about what is different from the dual pole side. Then what are their limitations? So let's go with MRMS mesh first.
Sure. So mesh is an algorithm. It's based on the total storm's sort of presentation on radar. So it's not just looking at that one low level, or for example, it's looking at the entire storm. And it's based on a quantity that's known as radar reflectivity, basically how much of that signal is coming back to the radar when we send out those waves. And so what it does basically is it integrates or sort of adds up the contributions from the radar scans starting up in the hail growth region, which is at temperatures below 0 degrees Celsius, so high up in the cloud, all the way up through the top of the storm. And then empirically, there's a study from almost 20 years ago now, or actually more than 20 years ago, that basically tried to empirically fit those values that they got from that algorithm to the reported hail sizes at the surface.
So take that. What do we know? What does it do well? And what does it not do well?
Sure. It's a great proxy for the storm intensity. So when you have a stronger storm, a taller storm, and one that's producing more precipitation particles, especially higher up in the cloud, that's really going to light up. So it's a great way for forecasters to see in real time, hey, there's something to pay attention about in this storm. I think it's also very good at hail detection. When the mesh value gets above some certain threshold, and people have been studying those exact thresholds, it's a very good indicator that, yes, there's probably hail in this storm. What perhaps it's not so good at is the actual hail size itself, even though that's in the name. The values that are spit out from this algorithm are in terms of hail sizes, either in inches or in millimeters, but those do not actually correlate very well to the reported hail sizes at the surface.
Yeah, that's some work we've done at IBHS as well. Kyle Ortega at the National Severe Storms Laboratory, University of Oklahoma, even some other folks there at OU have looked at this and found some of these kind of errors in trying to actually get to a maximum hail size, which we hear about a lot. And in the building science world, we want to take that to a damage state. But there's actually more to hail, right? That, lots can fall, lots of given sizes, those kinds of things. How does radar handle the concentration element plus a size distribution that it's sampling?
And therein lies the problem with radar-based hail sizing efforts. We're limited by the physics of electromagnetic radiation scattering off of those particles. And so effectively the amount of radiation or the amount of signal that comes back to the radar is proportional to both the number concentration, so how many particles there are per unit volume of the cloud, but then also very strongly with size. The problem though is that dependence on size changes as you get to bigger and bigger hailstones. It actually weakens. And so you may end up in a situation that you get the exact same amount of energy back from the cloud if you have a few big ones versus a lot of small ones. With the dual polarization radar upgrade, there are some ways that we can now look at the concentration of certain parts of that size spectrum, including the high concentrations of small hail, which is something that IBHS has been interested in recently as well.
Yeah, so let's go into the dual pole side. So there is an operational algorithm, hydrometeor classification. It does have a hail sizing criteria. Tell us a little bit about that, because both of these, the MRMS mesh and the dual pole based products, do appear into not only operational work, but also the application where we talk about hail swaths and looking at damage underneath that. So tell us a little bit about how those size buckets are really kind of broken out.
Sure. So the hydrometeor classification algorithm takes each radar pixel, uses all the information available from the dual pole radar, and determines what it thinks is the most likely type of particle that's there, whether it's raindrops or snowflakes or hailstones. And if it is detected as hail, then it classifies into one of these three size buckets, as you said: small or sub-severe hail, severe, and then greater than 2 inches, which we would call significantly severe. So 1 inch is the severe threshold. So below 1, 1 to 2, and greater than 2. And really, when we put that together, it was based on the physics of hailstone melting, which seems a little bit kind of strange, but there's a few wind tunnel studies from back in the 80s that looked at the melting properties of ice particles in the wind tunnel. And it was noted that the smaller hailstones tend to accumulate much more liquid water as they melt, and they kind of hold that liquid water and almost looks like a hula hoop, like a little torus around it. So they look like big raindrops. As they get bigger, it sheds that water, that liquid is shed off as raindrops, and the resulting particle ends up being a little bit sort of drier and looks more like a hailstone. And so using the information about where the radar beam is at a given scan, the temperature from the environment, and then those different properties of the small melting hail versus the larger melting hail is how it's sort of broken down.
So let's go now to the future. And I'm going to start with work we've done, well, together really at IBHS, is understanding hail shapes.
No boy.
So we've done all sorts of things. We've measured hail in multiple dimensions. We've also 3D scanned them. And to me, it's one of the coolest pieces of the hail field program that we've done. But tell kind of our listeners, how does that information about simply diagnosing a hailstone shape, how does that translate into what is the future of radar hail detection?
Yeah, this is really something that opened my eyes, obviously, when we started getting these 3D scans in. For those who haven't seen the true natural diversity of hailstone shapes, it's quite amazing when you start seeing these lumpy, loby things out there in the field. But yeah, all of those aforementioned algorithms that we just mentioned have either explicitly assumed that the hailstones are spheres or spheroids, which is kind of like a squished sphere. So very smooth, very symmetric. And that's very rare when we go out and look in the field. So using the 3D scans, we're able to actually now use some very detailed calculations to see what a radar would see in each case of having this lumpy or loby hailstone. We can rotate it around. We can sort of look at it with different radar wavelengths and really try to better characterize the true range of what we might be seeing out in the field from the radar.
Yeah, so I think, for us, it was one, using that to understand hail aerodynamics at IBHS, but Matt's taken this kind of work and really kind of turn it on its head from the radar application side, which it's been a wonderful partnership for us, but it shows you the legs that this kind of foundational work can actually have, spanning all the facets of hail. So looking ahead, as we've talked about what's there now, I'm going to ask probably I'd say $1 million question, but we know hail's more costly than that. So let's call it the $20 billion question. Are we ever going to be able to pin down maximum hail size at the ground using whatever kind of remote sensing tool there might be?
Maximum size, probably not, unfortunately. However, I do think that in some respects, the maximum size is maybe not the target that we're looking at. It's safe to say that the maximum size from any given storm is probably not truly measured, because you'd have to be in the right spot at the right time, and that's, even with the detailed field campaign, that's very unlikely. What I think we might have some progress in the near future is looking at sort of the most common hail size, or potentially the sort of bulk of the hail that may be damaging. And so we may be able to get some indication and say, okay, there's a whole bunch of hail of this particular size there, and that information could be useful from a damage perspective.
Yeah, I would make the case that perhaps from a correlation to actual damage states, that's going to give us a better approximation of what to expect at the ground. And so if you think about all sorts of industry applications, that can guide improved processing of claims, resource allocation there from the insurance industry. We can change, really refine risk modeling applications with the damage functions that are there. So there's a lot that can be done. And I feel like this week, we've seen the progress really start to take shape through the sessions we've had on hail in the recent North American Hail Workshop. So that's kind of been my take on what we've been doing. Turning to the forecast side, now this is an element outside of assessing damage and what happens after a hailstorm. We do know there's elements of preventative things we can do to prepare for hailstorms, perhaps moving vehicles under cover, take some mitigation actions. But we've seen a pretty bad year in terms of global injuries from hail.
Absolutely.
So we have those warnings, our severe weather warnings that come with this. Where are we in forecasting hail from an impact to society perspective? Where are we and what can we do?
That is a great question. I'm not sure if I'm most qualified to answer the certain aspects of that. I think we're at the point where we can do pretty good sort of assessment of the risk of a given sort of day, whether or not we would expect to have severe hail. I think we're making progress on determining the sort of nature of that threat as to whether it would be sort of marginally damaging hail to significantly damaging hail. And then the societal aspect is definitely something that I think there needs to be a lot more work, because right now the warning has just kind of come out. They may or may not have a size estimate in there, but we can probably do a better job of awareness about when the conditions are right, so people have a lot more time to sort of think about and prepare what they might end up doing.
Yeah, and we have an episode of this show, our disaster discussions, that'll cover some of the social science, human behavior aspects of how humans treat those weather warnings and what actions they may or may not take. You do storm scale modeling, trying to actually simulate these hail-producing thunderstorms. So tell us a little bit about that, and then we're going to kind of take another dive into how that could be used to understand what could go on at the ground.
Absolutely. So this has been a fun project over the last several years. And so essentially, the idea of trying to understand the environments of hailstorms and what different factors contribute to the different hail threats is really difficult for the reasons we talked about, from just the lack of the reports and the lack of the quality of the reports at the surface. And so instead, we have another option, which is we can create a hailstorm in a computer model. And so that's what we did. And it's really nice because you can turn the knobs and say, crank up certain elements of the environment that might be more or less favorable for hail production, and then see what happens. And so we spent some time putting together a very detailed, what we call a hail trajectory model, where we can basically seed the storm, and each of these little particles can then go through and be kind of advected, as we say, or blown around by the winds, and grow into hailstones. And we track them all explicitly. We can do millions of these particles for every storm that we do. And we've really been starting to map out the parameter space of trying to understand how things like the changes of wind speed and direction with height might affect the hail production in a storm, or the amount of fuel, or what we call instability, can affect the way that hail is produced in storms.
Yeah, I think this has given us some great insights as to what's really going on within a thunderstorm. We can't just, we don't have a storm penetrating aircraft. We can't go take a look at some of these things. And just like we do at the IBHS research facility, we get to turn the knobs in our big full-scale test chamber. This is exactly the same thing. You can actually hold a whole bunch of variables constant and turn one knob and see what's going on. And we do the exact same thing. Thinking about that element, are we starting to kind of hone in, or some of the things you see in the modeling element starting to show up in the field?
Absolutely, and this is something that got me very excited this week at the conference. We're starting to see these areas of different features of the environment that maybe we hadn't considered before as a community. And now when we're starting to look in those directions, there's been a number of studies that have started to support what we see in the simulations. So it seems at least there's some broad consistency there. So we're starting to know where to look and what features may be important. And so we've got lots of great colleagues around here that they're working on these exact problems.
Yeah, so let's go to that one. It's a question we asked Julian. We have definitely seen, whether you call it a resurgence or a renaissance in hail research, really over the last, probably say 10 years, maybe a little bit longer. In your mind, what's actually driven that?
That's a great question. A lot of it was, at least from my own personal trajectory, has been sort of serendipitous. You've known me for a while, so you kind of see all the things that I do. I kind of get interested in various topics, but hail has always
snow is one of them too.
Exactly,
for our listeners. Yes, Matt does like his snow.
Yes, so anything that falls from the sky, I get excited about. So hail's always kind of been something that has fascinated me ever since I was a kid. But I think we're at this sort of convergence between when we're starting to see a big socioeconomic pressure. We're seeing just huge increases, as we've already discussed, and as Julian discussed, huge increases in that side. But then we're also pairing that with sort of the emergence of new technology. So we have the dual polarization radars that have come online that are giving us a huge new wealth of information to study hailstorms. The computer technology is advancing, so we can do these types of really high resolution, detailed simulations. The 3D laser scanning that you introduced has opened a number of doors for a variety of topics as well. So we're really just at this point where these new tools and these new data sets and these new capabilities are really sort of driving a lot of excitement in the science community.
Yeah, so it's been really a fun ride just for myself. And I will say, I've spent the better part of the last 7 years trying to not look like an idiot in front of this guy. But if my contribution is the 3D scanning, I think I could hang my hat and be happy. But it's been a really neat 10 years to see the research really ramp up. And we had some great student presentations this week. So I think we're in good hands with our next generation that's coming along to hopefully carry on the torch. As we kind of start to kind of wind down and wrap it up, we know hail's become almost a $20 billion problem. What do you think? How should we look at allocating resources to this? We talk a lot about life safety. Hail's not necessarily considered one of the big life safety elements, but when we throw in that property part, life and property, we can't ignore the dollars that are being spent every single year. A very good example from Varus was last year in a low hail year. We still had 16 plus billion in damage. So how do you view that? You have made some very wonderful comments in repeated sessions at this conference talking about trying to make sure we don't ignore the other perils that come with severe thunderstorms. We hone in on tornadoes, but what do we got to do? Let's think broadly now, outside of just tornadoes, but include hail, flood, all that. What do we have to do?
From the science perspective, I think you have to get people excited about it. I know there's a lot of people here focused on tornadoes. I've probably made a few not so good friends here if I keep saying that at the different sessions that we've had. But yeah, I think that highlighting the fact, and a lot of the people that study hail are making this point repeatedly at the beginning of each of our talks, just to raise awareness. I think that's one thing, is that a lot of folks who aren't necessarily plugged into the insurance sector or into sort of the building codes and things like that don't really realize what's at stake. And honestly, it comes down to the sort of decisions that are made at the national level in terms of funding agencies and in terms of operational meteorological agencies. What are they interested in? What do they see as being the drivers of their biggest problems that they have to deal with?
Yeah, we'll keep going on that one. One of the big pushes now is taking research, turning it into operate. R2O is the fancy name, but also in our private sector world, it's research to an application. Mm-hmm. So how do you see that evolving? What's the process, and how does the academic side view the application element? And how do you actually approach that from foundational research, thinking out toward what might be a future application?
That's a great question. So I always sort of have that in the back of my mind. Obviously, I do some stuff that's a little more esoteric. It's in my thermal energy transfer coefficient paper, for example. But ultimately, right, these ideas are to try to improve something in the long run, whether it's improved forecasts of hail, improved detection and being able to warn people about it, better characterization of the hailstones themselves, right, can feed directly back into some of the lab testing the IBHS does. So I always try to kind of keep that in the back of my mind about just whatever questions we're asking. It's always trying to improve something down the road.
Yeah, I think that's one of the critical elements now, is taking foundational research, understanding where it may be used, and really you think about wanting to put things on a level playing field out there, but also be able to foster somebody else who could take that application and run with it and turn it into something useful.
Exactly. That's really one of the dreams of people that do science, is we hope that someone can find what we do useful. If we're doing something that no one cares about and it isn't useful, then why are we doing that? So it's always exciting when people can take that and run with it and do great things.
Yeah, absolutely. We'll keep going more kind of on a weather thing. I might actually turn back the clock. So I'm going to ask this guy, how did you get started in weather? What was your...
Oh, wow.
What was the impetus for you to get into the weather world?
Hurricane Andrew, 1992.
Wow, we share that very much in common. You grew up in Maryland, is that right?
Maryland and Virginia Beach. Yeah.
Okay.
Yeah.
So why Andrew?
It was the time when I was of the age when I started sort of paying attention. So even before then, I wanted to be an astronomer. So I'd always been interested in the sky. Some of my most detailed memories from when I was 4, 5, and 6 are from bad thunderstorms that we had. My family moved down to the Virginia Beach area in 92, and that was the summer that Hurricane Andrew hit Miami. So I was just kind of glued to the TV, the Weather Channel, watching the coverage.
It sounds eerily familiar.
Yeah. And so it sort of switched at that point, just kind of seeing what nature was capable of and sort of how it affected people. And I honestly didn't get into hurricanes for whatever reason, but that's just sort of sparked an interest in our atmosphere and what can happen.
Yeah, so I had a sort of similar experience, but this one was an interesting one. My dad showed me the 1985 Nova tornado episode, and it had Howie Bluestein and Lou Wicker was a graduate student. These are all, for us weather nerds, we know these people. And
who are here this week.
Oh, yes, who've been here this week and we've gotten to work with in the field. And that kind of triggered my interest in weather. But like you, Hurricane Andrew, its final landfall was in South Louisiana. And so that really set myself on that path. And I did go into the hurricane world academically. And now Matt and I, our paths have crossed, and hail is the common thread for that. I do know the moment you kind of got involved with IBHS was with Tanya, my wife, Tanya Brown Giammanco, when she was at IBHS. I think she just grabbed you at a conference, or you guys just happened to cross paths. And 7 years later, here we are. So how about, what do we do in the next 7 years?
Wow. Yeah. Well, clearly we definitely need to continue getting the high quality data that IBHS has already been collecting over the past 7+ years, actually now at this point. The number of data sets, the number of people who have cited IBHS data collections and data sets at this conference so far is pretty astounding. So continuing to get these types of data that we can't get otherwise can really help push the science forward, as we've already seen. I think there's some very exciting work that our colleagues are doing, some of which we saw yesterday, for some new technology that's coming down the pipeline to even sort of push the envelope with what we can observe. And yeah, just to kind of keep asking questions, right? Just kind of keep pushing along and trying to see what's going on. The session that we were just in had nothing to do with hail, but one of the last speakers said a lot of stuff. And I was like, my mind started spinning. And so, yeah, just this type of interaction and just continuing to kind of push the envelope in our understanding of technology.
Yeah, I had that moment earlier today with a new term I learned about diagnosing curvature in a path. And so immediately I start jotting down how it might be a more efficient way to even diagnose hailstone shapes from just 2D imagery. Can you trace paths around a stone and look at the amount of curvature? So something completely unrelated to hail, wasn't about hail, but of course I start taking absurd notes, and I'll have to decipher that later. But I think the common theme, though, as we look ahead is one, we can lead with observations, but we got to have both. We got to have the modeling element, and we got to have the observations in the field to make sure what we're seeing in the model is showing up in the real world. And if there's things that look weird out in the real world, that we can actually go back and simulate and figure out what's going on.
Absolutely. Yeah.
So that to me has always been kind of a unique element of science that I've always gravitated to. That everything works hand in hand. And at IBHS, in our experimental test world, it's the same thing. You take observations from the field of building performance. Can you simulate it in the lab? Can you understand what's happening and be able to diagnose solutions? Solutions, identify problems, come up with solutions. So that's a very similar theme, I think, throughout the natural hazard sciences. So as we kind of take our way into the end land of hail, tell us a little bit about some of the other areas of research that you do. I want folks to understand that you are a kind of a well-rounded scientist. Talk about a little bit of the winter weather pieces and parts that you do, and how that may have an impact on society.
Sure. So as you said, I'm a bit of a nerd when it comes to weather. So anything that falls from the sky, I get excited about. A lot of my research is focused on radar as sort of the centerpiece, radar and precipitation physics, as I like to call it. So one of the things that we've been getting into recently, my wife, Kelly Lombardo, is also a professor at Penn State. We've been looking into snow squalls.
That's another element too. I get to work with my wife for quite a while.
And yeah, snow squalls in terms of a hazard for society. I mean, every year we end up having crashes on I-80, big pileups because of these things. So we're trying to work to understand the formative mechanisms that drive them, as well as the environmental factors that support them, so we can improve the forecast and warnings of those as well. Yeah,
I think winter weather, actually, we've kind of pivoted topics now a little bit. Winter weather is an area that doesn't necessarily get as much societal impact attention, but we've seen kind of the detrimental effects. You hit the auto side, the road weather. We saw significant impacts from Arctic air outbreaks in the southeast, which simply are the way we build buildings are not meant to have to withstand extreme cold, especially when the infrastructure fails. So there's an element there that we talk about a bit at IBHS, but I think warrants some new work to understand how do we start kind of whittling away there. It's something, the winter weather element that people may not think about. I mean, we used to talk about hail as the Rodney Dangerfield of perils, like it doesn't get any respect. I think that's completely changed now, mostly because of that big dollar number. But I think you hit a touch on the winter weather element that people outside of those areas that are prone to this may not think about. So it's been a wonderful conversation with Dr. Matt Kumjian from Penn State University here on our AMS Severe Local Storms Conference series. I want to thank Matt for joining us here today. In our hail series, you've heard from Julian Brimelow, Executive Director of the Northern Hail Project. We followed that up with a little bit of futuristic look at what we can be doing in hail research. So thank you for joining us, and we'll see you next time on Disaster Discussions.
Thanks for listening to the Disaster Discussions podcast, an IBHS production. Subscribe to our podcast on your favorite podcast app, or watch the podcast on our website at ibhs.org/Disaster Discussions Podcast and the Insurance Institute for Business and Home Safety YouTube channel. Connect with us on our social media pages on Twitter @Disaster Safety, Facebook at facebook.com/disaster safety and on Instagram at IBHS_org. For more great content from IBHS, including ongoing research efforts happening at our facility, episodes of our podcast, and more, visit IBHS.org.